In today's video, we're going to explore a new way of thinking about energy that's called enthalpy. It's more useful for chemistry because it eliminates from consideration work, which often isn't something we want to quantify in chemistry. So to get the idea of what enthalpy is very difficult. Actually, it took me a long time to figure this out, and I've come up with an example that I think will make it easier to understand. Enthalpy is what's called a non-sensible unit. It's not something that you can sense directly, because it's defined in a sort of a mental way, not in a physically understandable way. But I think I've come up with an example that will make this easier to do. We'll start out this example by imagining that there's a system for which the only kind of work that can be done is pressure volume work. And this isn't actually too esoteric, because this is really the case pretty often in chemistry. For a system like this, it makes most sense to think about the first law of thermodynamics as delta E equals Q plus W, which is heat plus work. But since the only kind of work that can be done is pressure volume work, and we've quantified pressure volume work as minus P times change in volume, we could rewrite the first law of thermodynamics this way. Delta E is Q minus P delta V. Now we're going to look at two examples and see how the amount of heat that's measured will be different in two different cases. What we're imagining here is a rifle that's fired inside a calorimeter. So here's our calorimeter. You can see that there's a thermometer here that can measure the temperature, and this is a water bath or oil bath or something that has known specific heat. And then here's a very crude schematic version of a rifle barrel. Here's the cartridge that contains the gunpowder, so the explosion is going to happen in there, and then this is the bullet that could move down this barrel, and the barrel's open to the outside world. Now, the first example we're going to take a look at is a normal rifle just being fired inside of a calorimeter. Watch what happens. The first thing that happens is there's a detonation of the gunpowder, and that releases a good deal of heat into the water bath. But the second thing that happens is work is also done. The bullet moves down the barrel, and energy is transferred from the system in the form of work. Well, the Q that's measured here isn't all the energy that was released, because some of it was released clearly through working. The amount of energy that's been released here is what we call heat at constant pressure, or QP. And since that's very common in chemistry, chemists use a different term to describe that, and that term is enthalpy change. Enthalpy is the non-sensible quantity. It's actually defined in terms of energy, pressure, and volume. But I'm not even going to bother giving you the definition right now, because it's just confusing. I want to give you a kind of a gut feel for what enthalpy is. Enthalpy change, or delta H is the abbreviation for enthalpy, is the heat that's released under a situation like this, where work can be done. A sort of a crude and not very exact way of thinking about this is enthalpy is the amount of heat that would naturally be released as heat when some of it can also be released as work. So as we see in this example, the rifle bullet moving down the barrel can release work, and so the amount of energy that's released to the calorimeter isn't all the energy. It's just the part that would naturally be released as heat when work is possible. That's enthalpy change. Now we're going to look at a different rifle, and this is a kind of a screwed up rifle. Here the rifle is jammed, or maybe the bullet has been welded to the cartridge so that it can't move down the barrel. Now, I'm going to fire this bullet under the calorimeter as well, and here's what happens. There's an explosion, and some energy is released, but there's no work done because the bullet can't move down the barrel. So now we have heat at constant volume. The volume of this system doesn't change. The bullet is still there, and all of the gases are contained inside that cartridge. So this is Q sub V, or heat at constant volume. And when you measure this in a calorimeter, when volume is not allowed to change, there you're measuring all of the energy, not just the enthalpy. So a constant volume calorimeter measures delta E. A constant pressure calorimeter, which is how most heat is measured in chemistry, measures delta H, or enthalpy change. Now, because the second situation is so common in chemistry, we're going to work with enthalpy change much more often than we will total energy change. For a reaction system, the delta H, or the enthalpy change that we're looking at, is called delta H of reaction. The change that's taking place is a chemical reaction. Some reactions are exothermic. You've probably heard that term before, maybe even used in this class. Exothermic means heat is going to be released. So in those cases, the change in enthalpy is negative. It's less than zero. It's like a withdrawal of energy from the system through heat at constant pressure. So that's for an exothermic system. And delta H is positive for an endothermic system. In other words, that's an increase in the amount of energy available as heat from that system. So enthalpy is like available heat, or sometimes it's called latent heat. Heat that could be released or heat that would be absorbed in a chemical change at constant pressure. Enthalpy changes are reported in reference books and on websites and things under what are called standard conditions. And this is a little bit confusing because it's not really that standard. We just got done studying gases, and in gases the standard conditions, STP, were 1 atmosphere and 273 kelvins. Standard pressure is 1 atmosphere, and that's good to at least 3 sig figs. And the standard temperature is now 25.0 degrees C. When a change happens, or reaction happens, under standard conditions, we put a little degree sign after the delta H, and that means standard enthalpy change. In other words, enthalpy change when these conditions are met. So that sets the stage for talking about matter and energy together in chemical change. When we do that, we have what are called thermochemical equations. Thermochemical equations show the delta H, the enthalpy change, or the heat released, right alongside the change in matter. Here's an example of a thermochemical equation. When a mole of nitrogen reacts with 3 moles of hydrogen gas and produces 2 moles of ammonia, delta H is minus 92.4 kilojoules. That's a negative, so that means this is an exothermic reaction. So 92.4 kilojoules are released. If I were to flip this thing around, if I had 2NH3 gas, and that decomposed into a nitrogen mole and 3 moles of hydrogen gas, my delta H for this reaction would be the same value, but since I've flipped it around, it's not exothermic anymore. Now it's endothermic. And so my delta H would be a positive 92.4 kilojoules. So reversing equations changes their sign. Here's another thing I could have done with this equation. If I had a half a mole of nitrogen and 3/2 of a mole of hydrogen and 1 mole of ammonia, I would be taking the whole equation and cutting it in half. So that means half the amount of energy would be released. So delta H would be 92.4 kilojoules divided by 2, which works out to negative 46.2 kilojoules for delta H. There are some heats of reaction that are more important than others because of the way we have chosen to tabulate data and use it to solve problems. And these are called standard heats of formation. So here's what formation means. It means 1 mole of a substance is formed from its elements in their standard states. Here's an example. When I write the equation for the formation of ammonia, the last way that I did it in those 3 examples, I have a standard formation equation. 1 mole of ammonia is formed, so that condition is met. It's formed from its elements, which are nitrogen and hydrogen, that's what it's made of, in their standard states, which is the gaseous state for both hydrogen and nitrogen. Now I have to balance with fractional coefficients. So 1 mole is formed from its elements. The elements are in their standard state. So that means this whole reaction is happening under standard conditions. So the delta H for this reaction is called the enthalpy change of formation, or the standard heat of formation is a more common term for that. And this is tabulated in reference sources, like you can find it on several websites online. You can find it in the back of almost every textbook and in the chemical rubber company reference book that chemists always used to use. This data is tabulated and you can use it for solving problems. So this is a standard heat of formation because it's the value for formation of 1 mole from its elements in their standard states. The mechanism by which we've solved these kinds of problems is called Hess's law. Hess's law says if you can write a reaction in steps, then the enthalpy change for the reaction is equal to the sum of the enthalpy changes for all the steps in the reaction. And this works because enthalpy, like energy, is a state function. So it doesn't depend on the pathway. You can rearrange the steps in whatever order you want to. State functions don't require any knowledge of history. Here are the rules for using Hess's law. First one is, if you reverse the equation, you have to change the sign of delta H. So here's what that means. Let's say I had a theoretical equation, A plus B, making a compound C. And delta H for this reaction is equal to 100 kilojoules, let's say. If I flip that around and reversed it so that C decomposed into A plus B, delta H for that reaction would be negative 100 kilojoules. Change the sign if you flip the equation around. The second rule, sometimes you're adding equations up, you're adding these steps up in the Hess's law calculation. If you cancel a species from both sides of the equation, like we did, for example, with electrons when we were balancing redox reactions, you can't do that unless both of them are in the same physical state. And here's why, because changing from state to state involves energy. And so here's an example. If I have A, and it's a gas, and it reacts with B, which is a gas, to produce C, which is a liquid. And then I'm adding that to another equation where C, which is a gas, reacts with D, which is another gas, and produces E, which is a solid. If I'm going to add these up, I cannot do this. I can't cancel C from both sides because it's in the liquid state here, but it's in the gas state here. When it's in the gaseous state, it has more energy stored in it because you have to boil it to get it there. So they have to be in the same physical state or you can't cancel them out. Another rule for using Hess's law is anything that you do to the coefficients, you must also do to delta H. So again, when we were balancing redox reactions, we would often have to multiply one of the half reactions by 2 or 5 or 10 or something to get the electrons to cancel out. When we're doing that in thermochemistry, if you multiply the coefficients by some number, you have to multiply delta H by that number as well. So if I have A plus B, and that makes C, and delta H for this reaction is 100 kilojoules, if for some reason I need to double all the coefficients and make 2A plus 2B becomes 2C, delta H now has to become double, or 200 kilojoules. Now here's an example problem to show you how this works out, how you can add equations together to find delta H. You have this printed in your follow-along notes. It's kind of hard to visualize this whole thing on this screen. It's pretty crowded. We're going to work this out someplace else. So here's my objective. I want to get this equation, C2H4 gas plus water vapor makes C2H5OH liquid. That's my objective. And I want to find out what is delta H for this reaction. Well, I can do that according to Hess's law by adding up two steps or two other reactions. Here's what I'm going to do. I'm looking for anchors. I know that I want to have C2H4 on the left in the gas phase. So if I look at the equations that are available to me, I find C2H4 gas plus 3 oxygen gas becomes 2 CO2 gas and 2 water vapor. That has C2H4 on the left-hand side, so I'm going to leave it that way, and I'm going to record its delta H. Delta H for this reaction is minus 144.1 kilojoules. The other thing I notice is that I want to have C2H5OH on the right. That's another anchor. And I'm not going to worry about little things like water and oxygen and CO2 because I'm going to try and clean that up later or hope that it just takes care of itself. So I look at the second reaction that's given to me, and I notice that C2H5OH liquid is on the left. I want it on the right, so I'm going to reverse the equation. So I'm going to write down 2 CO2, because that's on the right-hand side, gas, plus 3H2O, gas, makes C2H5OH liquid. That gets it on the right-hand side of my step now, and 3 oxygen gas. And because I reversed this equation, I need to change the sign. It was negative 1367.1, So now it's positive 1367.1 kilojoules. Now let's look at what happens here. I have my C2H4 on the left, which I want. I have my C2H5OH on the right, which I want. I have three O2s on the left, and I don't want that in the first equation. But I also have three O2s on the right on the second equation. They're both in the same phase, so I can cancel them out. I don't want carbon dioxide on either side, but I have two CO2s on the left and two CO2s on the right. They're in the same phase, so I can cancel it out. I have water vapor on the right-hand side of the first step, but I don't want that in the overall equation. I have three water molecules on the left-hand side of the second step, but I only want one. Well, this also works out perfectly. If I take two waters from both sides, the water on the right disappears, and the water on the left is just one. So when I sum these together, I will find my overall reaction, the target that I was looking for. C2H4 gas plus one water vapor makes C2H5OH liquid. So what's delta H for this reaction? Well, by Hess's law, I just sum up the delta H's for the two steps. So it's negative 144.1 kilojoules plus positive 1367.1 kilojoules, which works out to 1223.0 kilojoules. That's Hess's law. Well, here's another one of these examples. This one's a little trickier because it's going to take four equations to be added up in some form or another to get your target equation. What you're shooting for is 2 C2H2 gas plus 2 water liquid plus 1 oxygen gas makes 2 acetic acid in the liquid form. Stop the video, give this your best try, and it's a little bit tricky, but if you use logic and common sense and follow your steps very carefully, you can use Hess's law to find this answer. Right, my target equation now is C2H2 gas, and I want a 2 in front of that, plus O2 gas, plus 2 water gas, makes 2 acetic acid, HC2H3O2, in the liquid phase. And my objective here is to find out what's delta H for this reaction. I'm going to pick out some anchors here. I know C2H2 is kind of a major compound here, not oxygen, not water, and the other one is the acetic acid. I want to make sure, first of all, that I have those in the right side of the equation and with the right coefficient on them. So the first thing I'm going to do is write down an equation that has C2H2 gas on the left. If I look at the equations that I'm choosing from, the first equation has C2H2 gas on the right. So I'm going to flip that equation around and write it this way. C2H2 gas plus H2 gas makes C2H4 gas. I want a 2 in front of my C2H2, so I'm going to double all the coefficients on this equation. So I'll put a 2 there, 2 there, 2 there. Now because I've doubled all the coefficients, I have to double delta H. And because I flipped it around, I have to change the sign on delta H as well. So delta H is going to be equal to 2 times a negative 174.464 kilojoules. Next, I want to get acetic acid in the correct place. If I look at the third equation, acetic acid liquid is already on the right-hand side. So I'm going to write that equation just the way it is. So that's C2H5OH liquid plus O2 gas makes acetic acid liquid and liquid water. I want to double all the coefficients, however, so that I have a 2 in front of acetic acid in the end. So I'll put 2 here, I put a 2 here, a 2 in front of acetic acid, and a 2 here in front of water. So because I doubled all the coefficients, I also have to double delta H. So that's 2 times a minus 495.22 kilojoules. Let's take a look at where we're at so far. I've got C2H2 in place where I want it. I've got acetic acid in place where I want it. However, I've got some problems. I've got C2H4 here, and I don't want it there. I have C2H5OH on the left, and I don't want that there either. I've got oxygen, but I have 2 moles, and I want only 1. I've got water vapor on the right-hand side, but I want water vapor on the left-hand side. And I've got hydrogen gas here that I want to get rid of. Well, I'm going to work on the big ones first. If I look at the second equation, I have C2H5OH liquid on the left-hand side, and I have C2H4 gas on the right-hand side. If I flip that equation around, I could cancel those 2 problems out by just writing that down. So the second equation, reversed, looks this way. C2H4 gas plus water liquid makes C2H5OH liquid, and I want to double this so I can cancel out 2 of each of those 2 problem species. So 2 there, 2 in front of water, and 2 in front of C2H5OH. Now because I doubled those and flipped them around, I have to have delta H equal to 2 times, not positive, but negative 44.066 kilojoules. Now let's take a look at where we're at. C2H4 gas, 2 moles cancel from each side of the arrow. The same thing with C2H5OH liquid. I'm rid of that problem. However, I put some water on the left-hand side, which is good, but it just merely cancels out the water that was already on the right, and I still have some problems. One of the problems is this. I have too many oxygen. I need 1, I have 2. The other one is I have hydrogen. I don't want any hydrogen, and I'm lacking water on the left-hand side. So how do I fix that? Well, if I look at the fourth equation, I can get water on the left, hydrogen and oxygen on the right to do some canceling. Here's how that happens. H2O, liquid, breaks down into H2, gas, and O2, gas, 1/2 of an O2. Well, I don't really want that. I want 2 waters on the left. I want to cancel a whole oxygen, and I want to cancel 2 hydrogens. So I'm going to double these coefficients. So the 1 in front of water becomes a 2, the 1 in front of hydrogen becomes a 2, and the 1/2 in front of oxygen becomes a 1. Because I doubled all the coefficients, I have to double the value of delta H. And because I reversed the equation, I have to change the sign of delta H. So delta H here is 2 times a positive 285.85 kilojoules. Okay, one last final check. 2 waters now appears on the left-hand side, which I want to happen. C2H2 gas appears on the left, which I want to happen. Hydrogen, not there anymore because it cancels. There's a hydrogen on both sides in the gas state. Oxygen, I have 1 oxygen on the right, 2 oxygens on the left, so the oxygen on the right disappears and this 2 becomes a 1, which is what I want. What's on the right-hand side? Everything is canceled out. Every species is canceled out except 2 acetic acid, which is what I want. And it's in the liquid state. Well, I've achieved my target equation by adding up 4 steps. So delta H is just going to be the delta H for these 4 steps added together. Well, 2 times negative 174.464 comes out to negative 348.528 kilojoules. 2 times minus 495.22 comes out to negative 990.44 kilojoules. 2 times negative 44.066 comes out to minus 88.132 kilojoules. And 2 times positive 285.85 kilojoules comes out to positive 571.701 kilojoules. Now, if I add all that up to 2 decimal places, which is the precision that I'm allowed here, I come up with minus 855.40 kilojoules, and that's my answer. That's my delta H. Fortunately, they aren't always that difficult. In fact, they're substantially simpler than that. What we'd usually do is use heats of formation to figure these problems out very simply using Hess's law. Here's the idea. Imagine that you have a generic reaction where compound X becomes compound Y. Follow my reasoning here. Compound X is made of elements. If I decompose compound X into its elements in their standard states, delta H for that reaction would be equal to the delta H of formation of X, only negative, because it's just the reverse of the formation of X. Then if I took those same elements, I would have to be able to make them into Y, because otherwise that would mean I was changing one element to another, and we know we can't do that. So if I took those elements in their standard states that I got by decomposing X, and I recomposed them into Y, delta H for that step would be equal to the delta H of formation for Y. Now when I add these two equations up, the elements in their standard state cancel out, and I'm just back to the starting equation of X becomes Y. So what's delta H for this process? Well, delta H for the entire reaction is just equal to the opposite of the heat of formation for X plus the heat of formation for Y. So we can generalize this, and we can say for any reaction, here's what we're going to get. I'll restate this. Delta H for a reaction is equal to the enthalpies of formation for the products, which are Y here, minus the enthalpies of formation for the reactants. And we can sum up the enthalpies of formation for reactants and products as long as we adjust them for how many moles are there. So at standard conditions, we can say that enthalpy change for any reaction is equal to the sum of the enthalpies of formation for the products minus the sum of all enthalpies of formation for the reactants. Now when you look up these enthalpy of formation values, you're going to find that they have units of kilojoules per mole, because remember, they're all for the formation of 1 mole of the substance. And so we're going to have to multiply by the number of moles that are in the balanced chemical equation from the coefficient to get the kilojoules for each one of these products and reactants. So here's an example. Find delta H for SO3 gas becoming SO2 gas plus 1/2 of an oxygen gas. So my reactant is SO3 gas. My products are SO2 gas and 1/2 mole of oxygen gas. The problem-solving strategy here for Hess's law says if I take the sum of all the heats of formation of products and I subtract the sum of all heats of formation for reactants, I'm going to get what I'm looking for, which is delta H for the reaction. That's my objective here. So my products are SO2 and oxygen. I'll have to find out what their enthalpies of formation are. So I'm going to find a resource on the internet and look this up. There are lots of places where you can find this. I went to About Com Chemistry and I found a table of heats of formation here. And they're in alphabetical order by compound, and so here they are. SO2 is minus 296.1, and SO3 is minus 395.2. Here's how this translates to this problem. My products are SO2 and oxygen. SO2 gas, in my equation, there's a 1 implied in front of there in the balanced chemical equation. So I'm taking 1 mole and I'm multiplying it by the heat of formation for SO2, which is negative 296.1 kilojoules per mole. Now I have to add to that 1/2 mole times the heat of formation for oxygen. But oxygen isn't formed from anything in its standard state. It's already an element in its standard state. So the enthalpy of formation for oxygen, well, there really isn't one. It's an element. It's not formed from anything. So that's the sum of enthalpies of formation for products. I'm going to subtract from that the enthalpy of formation for reactants. Well, my reactant is, there's only one, SO3. And the coefficient there is implied to be a 1 again. So, finishing this out, I'm going to put 1 mole times the enthalpy of formation for SO3, which is minus 395.2 kilojoules per mole. The moles are going to cancel out here. Oxygen, remember, disappears completely. And when I sum these up, I will get just units of kilojoules for the overall reaction. And for this one, it's positive 99.1 kilojoules, which tells me that this is an endothermic reaction. When this takes place, energy is going to be absorbed. We have one last topic here, and that is, how do we convert between delta E and delta H? Sometimes it might be important to be able to do that. So let me work this out for you. There should be a way to convert back and forth. We'll start out with the first law of thermodynamics. It says delta E is equal to Q plus W. And we've seen that when only pressure volume work is allowed, we can rewrite this as QP, Q at constant pressure, plus negative P delta V, because that's work. Or we could restate that as QP minus P times delta V. But QP is delta H. Heat at constant pressure is delta H by definition. So we could rewrite this. We could say delta E is equal to delta H minus P delta V. Now for an individual reaction, if you're just looking at the reaction, how do you know what the change in volume is? Well, we can on a per mole basis do this by looking at the balanced chemical equation. And here's how we can do this. V, we've just learned in the last unit, is equal to nRT divided by P. The only way the volume is going to change for any reaction system is if the number of moles of gas change. So we could say that delta V is equal to delta number of moles of gas times R times T divided by P. Volume only changes if the number of moles of gas change. So rewriting the first law of thermodynamics, we see delta E is equal to delta H minus P times, and now we're going to put in for delta V, change the number of moles of gas times R times T divided by pressure. Of course, pressure cancels out of this equation. And so here we get a conversion between delta H and delta E for any chemical reaction. Delta E is delta H minus the change in number of moles of gas times R times T. R we already know, and we're going to use the physics R, the 8.3141. It's 8.314 joules per mole Kelvin. And temperature has to be absolute temperature, of course, in kelvins. But how do we find the change in number of moles of gas? Well, we actually look at the balanced chemical equation. How many moles of gas are on the right minus how many moles of gas are on the left, and that's what goes in there. Let's do an example problem. Say we want to find delta E for this reaction here. Well, we saw that delta E is equal to delta H minus the change in number of moles of gas times R times T. What's the change in number of moles of gas here? Well, on the left-hand side, I have only a solid, so I have 0 moles of gas on this side. On the right-hand side, I have a solid, but I have 1 mole of gas. So 1 mole of gas on the right minus 0 moles of gas on the left gives me a change in number of moles of gas of 1. Let's put the numbers in. Delta H is 571 kilojoules minus 1 mole times R is 8.314 joules per mole Kelvin times the temperature. This has the little degree sign, so this means we're at 298.2 kelvins. That's the standard conditions. Kelvins are going to drop out, moles are going to drop out, and now I'm trying to subtract joules from kilojoules. Well, that's not going to work. So I'll multiply my kilojoules by 1,000 and rewrite this in units that are compatible. So delta E is 571,000 joules. I've just multiplied by 1,000 minus 1 mole times 8.314 joules times 298.2, and the kelvins are already canceled. To the nearest 1,000, this comes out to 546,000 joules.